Start this video, I just recommend you to watch the nyquist stability criterion part 2. I'm then tired already, so I'm not going to go through this video. But if you haven't watched, you just watch first, and then come back here later. So this part is actually actually you can watch, or I would suggest you watch. After you watch finish, you come back here. So if you were to come back here already, you can actually see that the closed loop system is stable if and only if the number of clockwise entanglement to the critical minus 1 point is equals to the number of right half plane open loop zeros. So if you still remember the right half plane, right? So imagine we have So imagine we have a real and imaginary, and then if you have a zeros in the right half plane, okay, you have some zeros over here. Okay, the number of if you were to draw a nyquist contour with a semicircle one, and you plot every point. Okay, you plot every point, then you translate it to the nyquist plot. Typically, you have some nyquist contour circulating around. I don't know the amount of entanglements. I have no idea how it works. As you say, the Cauchy's arguments principle states that the number of entanglements of the negative one. Okay, in this case, let's say this is negative one. So if you have a nyquist plot and you circle 3 times, 2, 3, right? You will have, this means what? Okay, 3 times plus whatever poles you have a number of zeros. So if I circulate 3 times plus, let's say for my transfer function I see that it's 1 pole, so therefore I have 4 zeros, and in the right half plane. Okay, and yeah, so it should be maybe 4 zeros over here. Okay, so if I have 4 zeros over here, I will have 3 encirclements. Okay, let me redraw again. So it will be 1, 2, 3, and then something like that. Okay, it may be abstract and I may be highly probably wrong, but this is the concept. So nonetheless, from here, also one thing is that negative 1. Okay, because 1 plus GH is equals to 0. Okay, if you were to bring this negative 1 over here, you have GH equals to negative 1. This portion is also not clear, but however, it helps us to determine the true meaning of the negative 1 radius. Okay, this is negative 1, this is 1. Okay, so there's radius 1. So if your nyquist plot is within, let's say your nyquist plot is somewhat like that, you are safe. Okay, you are stable. If your nyquist plot is somewhat like that, and it encircles the negative 1 also, this is simply unstable. Okay, this is simply unstable. Okay. So if your nyquist plot is within this minus 1, it should be always the same. Always safe lah. Okay, and therefore this is also what we are talking about. It says that this is the nyquist stability criterion. It says that the closed loop system is stable. Okay, so what I plotted over here is actually the closed loop system. Whatever, but yeah, and then since and then it's if the encirclements, if around the negative 1 point is equals to the number of right half plane open loop zeros, it is stable. Okay, so if the right half plane open loop zeros is, let's say, in this case is 3 poles, if it encircle negative 1 3 times, okay, let's say nyquist plot encircle 3 times, 1, 2, 3, okay, this will be stable. This is stable. Okay, because it is so abstract, it is so hard to see. Because if I were to plot in my nyquist, this one you can see my transfer function becomes so big. If I were to plot it out, you see, I cannot even understand what the hell is going on now. Okay, so because you see my transfer function is so many zeros over here. I should have a lot of zeros, but I should have a lot of encirclements, but I lack of some information. This is why I cannot proceed. But nonetheless, you should understand that we are not talking about these definitions, so we are safe from this very abstract form. But let's come to here. Okay, let's come to here. The closed system is stable if we does not encircle the critical minus 1 point. That's all. Okay, because typically our system is always all the zeros and poles are on this side. Okay, we didn't have any poles or zeros in the right half plane, so that's why we didn't study any form in the right half plane. We just only study in this in the left half plane only. So therefore, if your system is within the minus 1, you should be stable. You must be stable. Yeah. So I've cleared away this portion. Hope that I didn't confuse you anything except the nyquist stability theorem itself. So a note is that you need to remember this one. Okay, you need to remember this one and this one, and then you need to state why we only look at this. And then you also need to memorize this one. Okay. The 4 things you need to memorize is what? Okay. We only talk about positive omega. If you can see last time all our frequency responses, we talk about hold on, we talk about the full circles, right? And then from so 1 point is from, am I lagging? Okay, it's from 0 to, as frequency varies from 0 to infinity, right? And then there is also 1 point is from 0 to negative infinity, right? So in our module, we only talk about the positive one. Okay, so we only talk about this positive one. And therefore this is what I say. We only sketch the positive. Because we know that the negative part is reflection of the positive. So you chillax lah, okay? And then the stability is determined by the behavior of the polar locus near the negative 1 point. So what this means is that if your locus is far away from the negative 1, okay, you are safe. Okay, so if let's say this and this point, which is safer? Okay, this is actually safer compared to here. Although this is also within the 1 radius, but this is much dangerous than this point over here. So this is what it is trying to convey. Okay, and then the third point, the first and second order system are always stable for all values of gain. Okay, so if let's say I plot, okay, I don't know what plot is this. So for example, kkk is equals to this only second order only right? So let's say I multiply a certain value of gain. Let's say I multiply by 100 times kkk. What do we have? Oh, great. Okay, hold on. In my nyquist plot, okay, when I plot the 100 times kkk, right? I just show you just now. If I plot my nyquist, okay, hold on a while again. You see, although my nyquist plot is this nice, but as you can see, it's already it crosses the negative 1 portion, right? So apparently, you see, it already crosses the negative 1 portion. So actually, you cannot. I don't know what the hell. But if I went to the responses, if I were to plot the responses, okay, this is the responses, and then my gain is actually 1000. Okay, my as you can see, this is pretty much stable. Okay, it doesn't move, right? Compared to the input, this is the input. Okay, if you were to zoom in a very zoom in manner, you can see the input is actually sinusoidal. Okay, but then yeah, as you can see, it is pretty much stable for a first order system. Okay, so if I were to introduce a second order system, let's say okay, what do we have? Okay, so I am lagging now. I am lagging terribly, so hold on a while. As you can see, Now if I were to sub in, it is a second order system. Okay, let me zoom in around. Okay, if it's a second order system, my output is also quite stable. If we have a 1000 gain, okay, it's just amplituding. It's just amplitude. It's the amplitude that changes. Now let's introduce third order. Okay, now this is third order. What do we have? So lagging. So then, never mind. So yeah, as you can see, it is not stable anymore. It is, go into some instability portion. It's not a constant sinusoidal anymore, right? It is, boom. It is not very constant sine wave anymore. So this is the stability concept. So first and second order system are all values of gain. They are all stables, okay? And then for for a third order and above, definitely they are all not stables, okay? As you can see, if third order is really that manner, okay? If third order is really this manner, how let's just see fourth order lah. If okay, so if I were to plot for fourth order, what do you see? It's also very unstable. So nonetheless, as you can see, 1000 gain. So for all gains, as you say, so typically I will choose the worst case scenario. So yeah. So for an open loop system, it has n poles and n zeros. Okay, so if the number of poles is more than the number of zeros by the order of 2, then the closed loop will be unstable. So if the pole is a lot more than zeros, the system is not stable for large enough gain. In other words, what do I mean? Okay, so if this is the case, okay, this is n, this is n, and this is m. Am I right? M poles. Okay, sorry, my fault. It should be n zeros and n poles. So in this case, n minus m is equals to 1. Okay, so if you were to cancel, in other words, we'll have, although they are not same, but in terms of order, okay, you have only first order, right? So in other words, if I say I have another s plus c, okay, if I cancel again, I only have second order. In this case, this is also stable, right? This is why, so let's say this is n equals to 1 and n equals to 3, right? N minus m, 3 minus 1 is equals to 2, right? It is still considered stable. As you see, n minus n has to be greater than 2. If it's equals than 2, it's alright, okay? So therefore, second order, as you can see, in our case, if it's second order system, because if you were to cancel away the orders, it's just simply saying second order only, that's all. And then if you were to, so if you don't believe me, let's say I plot a fourth order, this is third order, right? And then I increase another order, maybe. So this is the first order, and this is third order, same as this one. This is one order, this is third order. If I were to run it, it must be stable, okay? Because of the, okay. As you can see, good job, it's not stable, hold on. Okay, the gain itself is stable, okay? I may be wrong lah, just as you can see, the gain itself is pretty much stable across, increasingly stable, okay? Let's say if I were to furthermore increase now the number of poles has already crossed my, what do we see, okay? What will you see? As you can see, it is pretty much very unstable now. If I were to even set to time is equals to 1000 seconds, okay? You see, it is very unstable. It is totally not, you see, it is not ascending in a very same order. Comparatively, if let's say I set it to 1, and let's say we have fourth order, okay? as you can see, this is also the same thing. Okay, comparatively, as I said earlier, if it's okay, now this is two order in the zeros and fourth order in the poles. Okay, so definitely we should be stable, right? Stably growing also can. Um, troublesome. It's not shown much. Yeah, hold on. Okay, you know what? I'll just give up. Okay, I'll just give up. This is troublesome. Okay, I just need to memorize that for poles, if poles is more than zeros by greater than 2, for large enough gain is unstable, that's all. So you need to memorize all these fore and down points and nyquist plot. And the next video we'll talk about gain and phase margin. Okay, and then we'll talk about the rest of it. Yeah, I have spent a lot of time. I'm still haven't finished it. So this video sucks. Yeah. So I'll see you in the next video.